Okay. So what do we do? What are the next steps? So obviously, we think about the lecture and the kind of the wide-ranging impacts that Dr. Haas has mentioned. Certain things resonate with me. I think different things resonate with different members of the audience. And I think that's why we wanted to take a moment after important parts of the program today to get a perspective from some of our other laureates about what's the big deal. And so now that we've kind of talked about this call for action in education, to realize that sometimes it's not what you don't know that can get you, but it's what you don't even know you don't know. How do we solve these problems? What is the industry's response? How do we grow as students and practitioners in this field? And to do that, we wanted to bring up a Clarke Prize laureate so you can kind of take us kind of top level and go, hey, why is this important? Why do we need to understand this? What should I be thinking about as an individual practitioner? So we're going to introduce Joan Rose, who's the Homer Nolan Endowed Chair of Water Research at Michigan State University, and is also an international expert in water microbiology, water quality, and public health, and has investigated numerous waterborne outbreaks worldwide. She's published more than 300 articles and is widely regarded as the foremost authority on the microorganism Cryptosporidium. And with that, Joan Rose. Joan, thank you.
Thanks. Yeah, I followed that little, I always say Cryptosporidium was one of my mentors. Little microorganism there. So I thought I'd just give a global perspective here, and this will be pretty fast, and I'd like to then leave some time, because we have about another 25 minutes, to get some of your thoughts in this area. So, global trends in the Anthropocene. So we already know about population growth, but when you look at any parameter from about the 1950s forward, we have what we call the Great Acceleration. So you can put animals, eggs, pesticide use, and of course water withdrawals, and you start to see this acceleration. Until recently have we started to stabilize some of these plateaus in various parts of the world. And so we really dramatically changed our water cycle and our water resources and the quality of that water. And it's not just these issues, but it's the billions of people that lack the wastewater treatment, lack toilets. Even in my own neck of the woods, we've got a lot of on-site wastewater systems that are now known to be contaminating surface waters, as well as groundwaters. So we're got these great big challenges, and these are the major sources of these pathogens. I just read a report that came out of the FAO, and they said that animal manure is now the #1 source of nutrients and pathogens globally. And so we haven't even tackled animal waste comprehensively around the world, the way we've started to think about human waste. The other thing is we've changed our landscape. So we have cultivated the global landscape at a very large scale. That has changed over the last 50 years too, with a great acceleration. Commensurate with that is the de-acceleration of wetlands. So I worked in Florida, a state that had a lot of wetlands, and now I'm in Michigan, a state that had a lot of wetlands, and both of those states show the same trend. We have gotten rid of our wetlands, our buffers, and we've changed it over to ag, forest, and urban, peri-urban, rural landscapes. So we've really been changing things. Chuck's already mentioned the big deals, the big issues that are impacting public health. Besides emerging contaminants and antibiotic resistance, he's mentioned climate change, restoration of our infrastructure, our water infrastructure. These are very big challenges that we haven't really grappled with, I don't believe, at the scale that we need to. This is a scale issue. This is big, and it's not just in our own backyard. And it's everything from the watershed and algal blooms and new emerging pathogens and resistant cryptosporidium and to Legionella and new pathogens in our pipe system that we have not recognized. So we can have Legionella in tap water, and we can have Pseudomonas aeruginosa in tap water, and it still meets the Safe Drinking Water Act rules, right? You're not in violation of safe water. So what do you tell somebody if you find high levels of Pseudomonas aeruginosa? And what do you tell somebody if you find Legionella pneumophila in their water? And a lot of utilities will stand up in front of a community and say, guess what? We meet the Safe Drinking Water Act. Your water's safe. Now, I like visualization, and I think we should do more of that. I think we are going to have to learn how to plot changes in quantity and quality. Maybe we do a better job with quantity because it's a single measurement. But quality, of course, is more complex, because what are you talking about when you start talking about quality? We do have some maps of diseases. These may be, as you see in the cholera, that may be a single snapshot in a year of where the cases are showing up. Or it may be an average over 5 years of where is cryptosporidium in the world, where is typhoid in the world over a 10-year time frame of these cases. It might be associated with impact, like the rotavirus map. So we have some of these disease global maps, but we haven't merged spatial and temporal scales very well so that we can overlay them and understand what's going on, what has gone on in the past in the acceleration time, and what's going on now. So as Chuck mentioned, I tagged along with him and bugged him when I first started working in this area, because I could find a single virus. I was working in Mexico on environmental virology at a full-scale drinking water plant, and I could find a virus in 10 liters of water. I could find, and these were cultivatable viruses on cell culture, or 50 liters of water, 100 liters of water, and I did not know how to interpret that. When Cryptosporidium and Giardia came on the scene and I started working in wastewater and wastewater reclamation and moved to Florida, same thing. We could find these organisms, Giardia and Crypto. We look under the microscope. We don't know whether they're alive or infectious, right? We look under the microscope for those organisms. We could find them. We didn't know how to interpret that. So I tagged along with Chuck to learn about risk assessment, because I think it's a very powerful framework for bringing multiple disciplines together, bringing science, engineering, management, policy, stakeholders together. And I found it in my career very, very valuable as a scientist to work within that framework. And sometimes I'm working just in hazard ID. We look using new molecular tools and new pathogens are showing up. Working with the medical community and the animal community to look at dose response, and then those that can model that and give us a mathematical probability of infection. But where the real challenge is in exposure assessment. An exposure assessment means we have to characterize the source better, the distributions, transport, and fate. And I can tell you that I think we know very little about persistence and viability in the environment. And that we're very much lacking there. And we have the tools to bring it all together as a characterization. And now we know that we really should start with our stakeholders. Anytime we're using the framework, it is an interplay between who cares about this, what do we care? You know, when we say what's safe, that is a policy judgment. We determine what's safe by what we care about, what we're willing to pay. And we don't often have that conversation up front. And then look at the various options. And it is an iterative process, because once you go through these frameworks and you work with others, you learn something new. You have to go back and refine what you know and what you've done. Now, we have hundreds of hazards that are found in water, some that come from feces, some that don't. and a whole range of diseases. And we're learning more that these are chronic. I found it really interesting. I looked at diseases of the Civil War because they kept records of these young men that got sick. And they would get dysentery, and they would get measles, and they would get all these different diseases. And there's a great book that looks at about 15 battles. And the battles were lost because of disease. And lo and behold, there's a whole long list of chronic illnesses that these young men suffered afterwards. And they match what we know now about infectious disease leading to arthritis and other maladies, and it was right there in the records, from the Civil War. Here's young, healthy men after infectious disease developed all these chronic, lifelong illnesses. So it's pretty amazing. Our methods have changed. Now, we still use the indicator system globally, and they still use E. coli around the world to say whether we've got fecal contamination. But it is a very poor substitution, and we cannot use it in our risk framework. The resolution of the source of the pollution, the relationship with pathogens, the relationship with risk, the relationship with treatment technology does not exist. E. coli is there to show the zero. It's to show the zero after you've disinfected. And that doesn't mean there's zero viruses and zero crypto and zero Legionella. So I think that we should be promoting a much better database on pathogens in water using the new tools. Now, diagnostics are improving, and this is really exciting because we've gone from just E. coli to alternative indicators, and they're pretty inexpensive. The coliphage, I think, as a virus, it's a virus that infects E. coli. It's a cultivatable test. You get the result in 24 hours. It's pretty good as an alternative indicator. Clostridium spores have been used throughout as an alternative indicator to look at treatment beyond E. coli. So we have alternative indicators that are not that expensive, and we don't have to go to the molecular tools. However, the molecular tools are going to give us the ability to look at space and time. Spatial and temporal changes. And we've moved now from qPCR to what's known as digital droplet PCR. And this decreases the QA/QC. It increases our ability to duplex or multiplex more than one target. And it's based on a most probable number. It decreases interferences because you divide the sample out in all these little bubbles, and you do the PCR in each little bubble. And we're seeing this technology, this new instrument, which is an add-on to PCR, being used by more and more laboratories around the world. But we're also going to sequencing data, right? Real-time sequencing. And we now have a sequencer that's out there. It's in the research and development. You can hold it in your hand. Right? $1,000. It's being used and tested in the clinical world. It's got some error rates. We don't know how well it's going to work in environmental samples because of the background noise. It hooks up to your PC. You can put it in a little suitcase. They've taken it over to look at Ebola infections and other things. And this is going to be the future, where we can have a sequencer, $1,000. And then the question becomes, how do we interpret? How do we sample? How do we use that information for decision making within the risk framework? Like I said, I like maps. I like the source tracking tools because we can start to look at, is it coming from animals or humans? And this is going to be important in the future. Here's our map of our watersheds in the lower part of Michigan, showing where we have hotspots associated with the human sewage marker, correlated, by the way, with our septic tanks in certain watersheds. We also have been doing pig and cow markers. Base flow is in the winter. As you can imagine, in Michigan in the winter, nothing flows very quickly. It's kind of all just sitting there. The markers go everywhere when spring melt and summer rain comes. So we also have concentrations. We know where the hot spots are. but everything is flowing. And it spreads pretty quickly. And yet we don't really understand what that means in terms of risk or management strategies on the landscape. The other thing I really think that's going to be interesting is the global mapping efforts that are going on. Nika Hofstra is part of a group at the University of Wageningen in the Netherlands, and they're doing water quality global mapping. And this is very exciting on plastics, on nutrients. We've been working with her on pathogens. And this is based on global databases, population, disease incidence, who's sewered, what kind of treatment does the wastewater treatment have, discharge rates. We can create emissions. How much pathogen emission is there going on around the world? This is cryptosporidium emissions, and we can separate this out by animal emissions and human emissions. We can also go down to a national scale. So this is a global scale, 1,500 kilometer grids. You can start to go down to smaller grids when you get to the national scale data sets. This is the rotavirus. After this map was published, I remember the UK, a reporter from the UK called me about why the UK was showing up kind of red on this map, and was basically, this is rotavirus basically because they don't disinfect their sewage, and if you don't disinfect your sewage, you're not getting very much virus removal, right? So you get a little bit with secondary treatment, but not very much. So if you don't disinfect, you're not getting rid of those viruses. So that's where we're going to go. We're also going to be able to do scenario testing, and they've done, Nika's done some really interesting work showing what if we don't improve wastewater treatment as population, even as it's plateauing out, it's still growing. What if we don't improve wastewater treatment? These are based on some of the climate models that say population growth and other things that are going to happen globally. And we cannot keep up. We're going to be in the same status in terms of disease, of these types of diseases, unless we make a major investment in wastewater treatment. So I believe we must use microbial risk assessment. We can use better diagnostics. This feeds into the risk assessment. It should feed into management and ultimately into water safety. And so we need to be able to interpret the data we're getting with the diagnostics. I have some recommendations, and then I'll leave it to you to add some comments here. I think we use the framework. We need to be quantitative. We bring management policy, and we promote translational science. We need to use more advanced technologies. I call them water diagnostics. I'm not against compliance monitoring. I'm not against global standards. We're going to keep using standards, but we need better water diagnostics for better decision making. We've got to decide where our dollar goes. It's going to be expensive. And we need to support the development of these laboratories around the world that can use these new tools. They're going to be less expensive. They're going to be able to use them, and we can fill in our gaps spatially and temporally that we have now in terms of making decisions about safe water. So I want to thank my many collaborators that have helped, and of course all the students. And anytime you're at a university, you're working with a global group of students. They come from all over the world, and they want to solve the world's problems. So I think it's up to us to help them do that. Thank you. So who has a comment out there that they'd like to ask where we need to go? I mean, it follows up on what Chuck was saying on our T education frameworks and things like that. And how we get knowledge to practice, right?
Thank you, Dr. Rose. The creep factor kind of goes in when you see this kind of stuff. Just curious how our own body's immune or tolerance to some of these things, how that plays into these kind of studies, the superbugs that are out there and such, and how that's played into that as we, I don't know, take on more and more of these different foods and strains and cross strains, et cetera.
Yeah, so in the dose response function, we can start to look at the immune, the immunity and the role it plays in both in subsequent exposures and decreasing disease outcomes, or maybe even stopping infection, the next infection, so we know we do have some lifetime immunity of certain things. But we also have some of our chronic disease outcomes are associated with our immune system. So our immune system reacts to Campylobacter, Salmonella, we get reactive arthritis. So we have both of these kinds of things happening with our immune system. Now the global maps that we're looking at are based on infection rates that have been reported at the global level. So for example, in some country, there's 10% infection rate of Cryptosporidium. There's 30% infection rate of rotavirus. I worry a lot about the funds, the amount of dollars that have been spent on global vaccination programs when an equal amount should have been spent on water infrastructure, because let's just take the rotavirus vaccine for now. It's available, you can give it to young children. Its efficacy is maybe 80%. Mark Stotzi's here, he may know better than me about that efficacy. It's not being taken up in Africa where it's needed because of high mortality. They can't get to the doctor, so there's high death because it costs too much. And the campaign for polio eradication is huge. They still have poliovirus outbreaks, and that's a very effective vaccine. And yet, if we invested equally in wastewater treatment at the same time, we would have been controlling hundreds of enteric pathogens, not just one. So I'm not against vaccination programs. We can use immune status in our waste models to understand more about disease. But I think we just need to face the fact that, we're going to have these enteric pathogens around, and we should invest in sanitation and wastewater treatment. Hepatitis A is going on right now in California and spreading, and even though we have a nice vaccine that most of us have taken, the homeless are not vaccinated, and they don't have a place for adequate sanitation, and so hepatitis A is spreading around again in California when we thought we had that disease sort of under control in the United States. So I'd like to see an equal investment in technology that reduces exposure.
Hi, I'm Sir Perry McCarty from Stanford University, and I want to first second Chuck Haas's comments that we should get rid of the terms of unplanned and planned portable reuse, indirect, and so forth, and address all the waters that we drink in the same way. I think that, and what Joan said, are really where the water industry important. I'd like to go back a little bit, because the water industry has always been very careful, didn't want anybody to talk about their water being unsafe, and so they never really wanted to address that. But when Orange County came out with its very important pioneering work on water reuse, everybody started jumping over here. Well, how can you do that? We don't know anything about the pathogens. We don't know anything about all the core chemicals. They didn't want to do it for their own industry as general in the unplanned reuse, which was going on throughout the world, but they were really glad to jump over it when people talked about portable reuse. And so it really forced a lot of the research that went on, which became very important. So I think one of the things I always like to recommend and comment and thank is in the portable reuse research is where we got a long way ahead in the water industry. And now we understand, because of all that, now we really understand so much, and all the uncertainties that we have. We understand them. It is time to start addressing that to all waters and not just portable reuse water. So I want to thank the speakers, Joan and Chuck, for bringing these issues, and I certainly second them.